This lecture deals with the concept of work. It's not the concept of work that you might have, as in mowing a lawn, climbing a ladder, digging a ditch. The physicist has his own special definition of work, which I'll describe to you now with an illustration. A block was once there. A certain force, perhaps just one of many forces acting on the block, is pulling with a force magnitude F at an angle theta relative to the horizontal. The block was here. Later it's a distance x away there. The work done by this force, and this force in this equation and in this example is assumed to be constant. It doesn't change. The work done by that force is shown or calculated by this equation, F times x, where x is the distance traveled times the cosine of the angle theta. I'll emphasize that F and x are positive numbers. In past problems dealing with displacements, sometimes x could be positive, other times negative. And in the case of forces pointing to the right were taken to be positive and to the left negative. There are no negative f's or x's in our discussions of work calculated using this equation. F and x are always positive numbers. In the event that f is not a constant, as is required if you use this equation, then it's okay to use the average value of f if you know how to find that value. Not so easy in most cases, but in special cases, it's a simple matter. If the force as the object moves varies linearly in a straight line, regular fashion, then you may use the now famed middle value rule. You first encountered it when we discussed the average value of velocities way back in chapter 2. If f varies linearly, then f is the middle value, 1/2 of the sum of initial f naught and final unsubscripted f. Let's look at a graph that shows a linearly varying force. We have force measured in newtons on the vertical axis, distance moved along the horizontal axis measured in meters, force again on the vertical axis measured in newtons. We'll assume that the force that's acting on our object in this graphical example is parallel, points in the same direction as the motion of the object. So theta is 0, and by the way, the cosine of 0 is 1. And so we have a graph of force versus distance shown in red. From 0 to 2 meters, the force varies from 1 to 2. The work done by that force is found using the average equation. F bar is the average value. It's 1/2 of the beginning, which is 1, and the end, which is 2, multiplied times x, which is the distance traveled, 2 times the cosine of 0. This works out to be 3, and the units are the product of force units times distance units, newtons times a meter. A newton meter is one of the ways to represent the standard international unit of work done. The second part of the force is labeled B, or the time period over which it acts is labeled B. The force average is found easily enough using the middle value rule. Starting force at the beginning of the B time interval, 2 newtons. ending value 4 newtons. 1/2 the sum times the distance moved, again, it's 2 meters. Cos of 0, final result 6 Newton meters. The total work then done as the object moves from the 0 mark to the 4 meter mark is the sum of the two works done, 9 Newton meters. The Newton meter is a unit of work that we'll seldom use. There's a single word unit that stands in place of a Newton meter that we will use from now on. 1 joule, lowercase Joule, abbreviated uppercase J, will from now on stand in place of a Newton meter. So the final result, measured in the preferred standard units for work, is 9 joules.